This is Precal, it's lesson 2.1.1, and in this lesson we're learning about concavity and local and global max and minimums of graphs, and a little bit about some notation, like some shorthand notation. So the very first problem is 2-1, and it just shows a graph, and it says Riley decides to take a scenic drive. The graph shows Riley's trip. So we can look at this graph right here. So it looks like we have distance on the y-axis and we have time in hours on the x-axis. And so I'm just, like, we have to make up a little story about what this graph might be about. And so since they said it was a scenic drive, and since this is distance however far away from home, it looks like Riley's going pretty slowly, because you can see after an hour they're only 6 miles away from their house. I mean, they're driving pretty slowly, they're not on a freeway, kind of steadily getting away from home. Maybe, you have to make up a story, so maybe they're going to the lake, maybe they're going to Ellis Lake. It looks like they kind of like maybe go around a corner or something that causes them to get a little closer, causes Riley to get a little closer to home. This right here where it's flat, that would be maybe they stopped for lunch or something. I'm looking down here at the time, and I actually counted these out. It looks like every single one of these little two squares is 15 minutes, so it's like about 7.5 minutes per square. So anyway, they stopped for lunch maybe, and then maybe now we're going a little faster, and it looks like we're getting closer and closer to home. So maybe we're on the way home, but for some reason change our mind, and maybe we forgot to pick up our dry cleaning, I don't know, and so then we're going farther and farther away from home. Maybe we went to whatever it was that we had to do. We got there, did it real fast, and then now we come and finally we're home. So that's my story that I made up, but basically we're just getting some practice. We're going to use this graph now to talk about a couple different concepts, and one of them is problem 2-2. It says, when is Riley's distance from home increasing? So you'll remember when we described the graphs, it could be increasing or decreasing. So they want us to get this notation down. So I kind of highlighted where it's the graph is increasing, meaning it goes up from left to right. And so I'm going to say that x is in between 0 and that's 0.75 right there. Let me make this bigger. Okay, so this is how you can notate that. And I think you've seen this before, with these inequalities. And then also it's increasing right here where x is in between 1.5 and 2. So that's a notation they want you to use. And then they say, how is it represented on the graph? Well, we can say the graph's going up from left to right. I was going to say it has a positive slope, but it's not really linear, but it is definitely going up from left to right. So that's what they want you to say. And then letter B, when is Riley's distance from home decreasing? So we can look on the graph for places like that. I see like right in here from 0.75 to 1. So you can write, and I wrote it like this, x is in between 0.75 and 1. And then it's neither increasing nor decreasing right here where he stopped and had lunch. But you can say it's decreasing, that's 1.25 to 1.5, and that's how you write it right here. And then it's also decreasing from 2 to 2.5. Okay, and then it says, is the distance from home ever constant? Well, that is right here where it's a horizontal line. And so if I wanted to write that in I keep saying interval notation. If I want to like denote that interval using inequalities, I could say x is in between 1 and 1.25. Okay, so to make this a little shorter, we're just going to skip on down here to extrema. So extrema is points on a graph that are the high or the low point. So we have a local, you can have a local maximum or minimum or a global maximum or minimum. So we're going to look at the graph that we were working with earlier and identify some of those. So letter A says, look back at the graph. Which points are maxima? So maxima would be, like there's one right there, just the highest points. So that's actually going to be called a global max because it's the highest one on the whole graph. And then this is also a max though. It's when we call that a local max. And if I want to you know, say what that point is, I would say it's 0.75 comma 8. We could say it's 0.75 comma 8. So you can just use an ordered pair to denote the point, the max. And then this one would be what? 2 comma 5. So that would be 2 comma 5. That's how you would answer that if that was one of your homework problems. What else do we need to know? Let's find the minimums. So the minimums, this right here would be a local min or a local minimum, and that is 1.5 comma 1. And then the global minimums, there would be 2 of them because for the whole graph, 0 is the lowest you can get. So there's one here and there's one here. So I think that's pretty simple. Let's see, concavity. So we're going to talk about whether you've probably heard that word before, like concave, concave up, or concave down. So in our book, an easy way to think of it is right here in our book. It says a function is concave up whenever you can trace a cup or a U-shaped curve that's right side up. So I'm going to kind of get this blue pen and look where I think something is concave up. So maybe this is concave up. And it's kind of hard to, like, you have to just make a judgment call on when does it stop being concave up and start being concave down. Because if you can see where I'm drawing here with my pencil, the part that I just squiggled with my pencil, that's concave down, isn't it? So we got concave up, concave down. That's an inflection point. It's a flex point or inflection point. So I can actually write that in interval notation if I want to. I could say, like let's say I just want to do the part that I just wrote the squiggle on. I could say x is in between. That's 1.75 and 2.5. That's one place where it's concave down. Where else could it be concave down? Maybe between 0 and 1. It's also concave down. Okay, so I hope you get the idea about concavity from that. This video is already too long. So I think that should be enough to get you going on your homework problems.